Welcome everybody to this journal club co-sponsored by the Section on Genetics and Genomics and the Assembly on Allergy, Immunology, and Inflammation. We're going to be talking about the paper Polygenic Risk and Rare Variants and Endotypes of Idiopathic Pulmonary Fibrosis, a genetic analysis of population-based and case-controlled cohorts, published in Lancet Respiratory this year. So this journal club is being recorded. It'll be posted on the ATS website. If at any time you have questions, feel free to use the Q&A function. Our speaker today is going to be the senior author on this paper, Dr. David Zhang, and our panelists are Doctors Christine Garcia, Deji Adegunsoye, and John Kropski. Let me just briefly introduce Dr. Zhang. He's an assistant professor of medicine at Columbia and a pulmonary and critical care physician. And his research focuses on ILD. He sees patients in the ILD clinic at Columbia, manages connective tissue-related ILD, hypersensitivity pneumonitis, IPF, post-COVID fibrosis, and many other conditions. And his research focuses on basic and translational research using next generation sequencing technology on patients with ILD, including those with IPF. I'm going to turn it over to Dr. Zahn now, if you want to go ahead and take it away.
Okay, thank you, Matt. And thank you to all the participants for joining. We're really excited to be able to share some of our work today. Here are my disclosures. So brief intro, idiopathic pulmonary fibrosis is a devastating progressive lung disease that is clinically heterogeneous, but invariably progressive. It's also a very difficult disease to diagnose correctly, which captured in real world settings by the significant median diagnostic delay of about 2 years, reproduced in multiple studies. And despite FDA-approved therapies, median survival remains poor, about 3 to 5 years even on treatment. And this is because current treatment does not reverse or stop disease, it only delays its progression. Part of the reason treatment outcomes were so poor is because a lot remains unknown about who gets this disease and why. One clue to the etiology of IPF comes from genetics, which stems from the observation that about 1 in 4 IPF patients have a family history, another relative with fibrosis. And over the years, genetic studies have found common and rare variants that increase the risk of IPF. On this graphic here, common variants are shown here with a very common variant allele frequency in the general population, but a small and low effect size. Opposite this is rare variants, which are rarely found in the population, but have a very high effect size, often found in families with this disease. Despite these advances, however, the known genetic risk variants really explain a small minority of the heritable risk of IPF, meaning that much of the genetics of IPF remains unknown. Nevertheless, the genetics have helped pinpoint relevant biologic pathways in IPF, one key pathway being telomere biology. Telomeres are protective DNA caps at the end of each chromosome, which help safeguard against genomic instability, and they shorten naturally with age or pathologically with rare mutations or chronic stressors. The link between IPF and telomere biology comes from a few observations. One, both rare and common IPF risk variants are found in telomere maintenance genes. Here's early work from Christine Garcia's lab showing that rare TERT and TERK mutations that decrease telomere length are found in probands of familial pulmonary fibrosis. 2, common variants can associate with telomere length, and Mendelian randomization studies that leverage this information find short telomere length itself to be causal for IPF. Here is a genetic association of those variants linked to IPF specifically and not COPD. And 3, short telomere length can occur regardless of rare variants and predict poor clinical outcomes. And this has been shown independently through multiple studies over the years. And so this led us to think about IPF genetics in a different way through embracing disease heterogeneity. And so instead of the conventional approach of identifying and assigning each genetic risk factor to disease overall, we wondered if we could discern intermediate pathways that the genetics are hinting at to define different genetic endotypes of disease. With what we know about telomere biology, we conceptualize 3 endotypes. One group that carry clear high-risk rare mutations, often in telomere-related genes. Another that have short telomere length but no identified rare mutation. and the third that has neither rare mutation nor telomere shortening. This classification turns out to be also clinically meaningful, with different endotypes having different survival curves, which is shown here using internal data, but also independently replicated many times. Another benefit of studying telomere length is that it's something we can study in anyone. And in contrast to IPF, which is a rare disease which limits the power to study its genetics, the genetic studies of telomere length, a causal molecular trait, has been done already in hundreds of thousands of people and yielded rich genetic findings, some of which are clearly starting to overlap with IPF. Here are Manhattan plots from two such GWAS studies, one of IPF on the top, the other of telomere length on the bottom, and highlighted in red are the top shared genetic loci for both traits, overlapping telomere-related genes, which is especially impressive since this IPF GWAS study only had 16 genome-wide significant hits, 3 of which already overlap with telomere length. So with this information, we wanted to address a few key questions in our study in response to some limitations that we perceive in the field. First, we know that most IPF genetic studies focus on either common or rare genetic risk. Could we, by examining common and rare variants together, improve IPF disease prediction? And do common and rare variants compete or cooperate to confer IPF risk? Secondly, most IPF genetic studies focus on all-comer IPF cohorts. Could we leverage heterogeneous disease endotypes to uncover additional IPF genetic risk? And can studying the genetics of causal traits, for example, telomere length, improve genetic understanding of IPF itself? To answer these questions, we utilized 2 case-control cohorts where IPF was defined from clinical expert centers, one from Columbia and UT Southwestern, as well as the IPF-NET clinical trials, another from TopMed, and thirdly, the large population-based UK biobank where IPF status was determined through ICD-based codes. In total, we included over 4,500 IPF cases and 400,000 non-IPF controls, all unrelated. Our study design, for our exposure, we examined both common variants and rare variables. For common variants, we focus on the large effect size MUC5B risk SNP. We focus on an IPF polygenic score that excluded the MUC5B SNP as well as overlapping telomere-associated loci, something that I'll explain in the next slide, and a telomere length polygenic score. For rare variants, we assess all of these in aggregate, also in disease-associated genes that were determined a priori. The outcome of the study was IPF status, either clinically diagnosed or ICD-based, or IPF endotypes, again, stratified by the presence or absence of rare variants and the presence and absence of short telomere length, compared against non-IPF controls. We performed a cross-sectional analysis of these 2 case control and 1 observational cohort studies to identify genetic associations and prediction of IPF and IPF endotypes. And for additional analysis, we compared the genetic liability for each genetic variable and assessed genetic correlation between IPF and associated traits. A brief note on polygenic scores. These are scores that sum up the effects of many common variants found from published GWAS studies. There are many diverse approaches to generating these. For our primary analysis, we chose a simple pruning and thresholding approach, choosing variants that were exceeding genome-wide significance. For the IPF polygenic score, we excluded the MUC5B SNP because of its outsized effect consistent with prior studies, and we chose to exclude the 3 overlapping telomere-associated loci because we really wanted to untangle genetic loci that were specific to IPF versus telomere length. To be fair, we performed several layers of sensitivity analysis whereby we redistribute the 3 overlapping loci. And we also assess a telomere polygenic score with fewer SNPs based on an older GWAS study, as well as a more robust IPF polygenic score validated and developed using lasso regression containing many more SNPs. Our primary approach was to perform multivariable logistic regression for predicting IPF. We examined several models for this. We examined a model that contained only clinical variables of age and sex. We examined a model containing clinical variables plus individual genetic variables, as well as a model that contained all clinical and genetic variables together. We also assess models for predicting specific endotypes of IPF using those individual genetic variables on top of clinical variables. We assess model performance by by calculating area under the ROC curve and comparing model performances using the Long's test.